Hello, welcome back. In this video we're going to talk about implicit methods for ordinary differential equations. In the previous video we described explicit methods such as Runkerkuta methods or Taylor methods. In this video we're going to talk about implicit methods and in particular we're going to focus on Hermite integration rules. So let's consider a simple ODE of the form u dot equals f of u and t. So u is some function of time, and u dot is the derivative with respect to t, time t. And we're going to use this shorthand notation like u of tn is un. So by the fundamental theorem of calculus, we can integrate this equation over a small time interval from tn up to tn plus 1. And we can directly integrate u dot, and it will be un plus 1 minus un. And then we have the integral of f with respect to time here. And remember, f can be a function that depends on u, but it can also depend on time explicitly. So let's suppose, for example, that this function f is a linear function of u. So in this case, we have a prototype differential equation of this form, u dot equals lambda u, which is a linear equation, and we know that the solution can be written very simply in terms of the exponential. So if u is u0 initially, then after some time t, the solution is e to the lambda t times u0. Okay, so this is the analytical solution, but suppose that we wanted to solve this equation numerically. Then the first step would be to use the fundamental theorem of calculus to write this differential equation as an integral equation for a small time interval, and then approximating this integral using a Hermite type rule that we have learned in the earlier video on numerical integration. So the lowest order rule that we know of for this type of integration is the trapezoidal rule. So this integral is approximated by the height delta t times the small base plus the large base of the trapezoid divided by 2. The next approximation to this scheme would be the Hermite rule. So in this case, we have the trapezoidal rule plus a correction, and the correction is the derivative of the function we were integrating. So it's delta t squared over 12 times the time derivative of this function at n plus 1 minus the time derivative at n. So these are the two extra terms. And this scheme is fourth order in delta t, whereas this scheme of the trapezoidal rule is second order in delta t. We can take advantage of the fact that u dot is known exactly from the differential equation itself. So we know that u dot is lambda times u. So we can use the differential equation itself to improve our scheme, and we can substitute this directly here. And then u dot will become lambda u, so we pick up a lambda squared term here. And then we have u n here and un plus 1 here. Okay, so this is what our scheme looks like. And you can march forward and integrate this in time by simply doing a do loop. However, the problem you see now is that un plus 1 is the next time step, un is the previous value in the previous time step. The problem is that un plus 1, the future value, is on both sides of the equation. And that's an unknown. We know the previous step, but we don't know the next step. So in general, if f is a nonlinear function, you would have to iterate this equation until it converges to a fixed value. So that would be a fixed point iteration or a self-consistent iteration. Or you could do a Newton-Raphson iteration. In this case, if f is a linear function, then we can very easily just solve this for u. And this is what we're going to do today. So in this video, we will focus on linear functions f. Okay, so let's try and solve this equation for the next step. Okay, so I simply copy-pasted this expression, and let's write equals here, and let's try and solve this equation for the unknown un plus 1. Okay, so this is the solution. We can simplify it. So we can pull un outside. And now we can do a similar thing for this equation. So let's try this. We just have to add this correction term here. And then just solve this equation for the future time step un plus 1, which is the unknown. And we get this expression. Before we implement this scheme and evolve numerically, let me just point out what this means. So if I calculate the Padé approximant of the function e to the lambda delta t, and I ask for the 1, 1 approximant, then Mathematica can automatically calculate this approximant. So if you don't know what this means, you can look at the documentation. Padé approximation is a rational approximation which expands your function to a fraction of two polynomials, one polynomial in the numerator and one polynomial in the denominator. So the 1, 1 approximation means we have a first order polynomial in the numerator, first order in the denominator. If I request a 2, 2 approximant, then I have a second order polynomial here, a second order polynomial here in delta t. And the next approximation would be 3, 3, so that would be third order here and third order here. And by now we start to see that this is what we get with the trapezoidal rule. It's un times this factor. And with the Hermite rule, we get this approximation. And with the Lotkin rule that we learned earlier, so the Lotkin rule would involve an equation like this. Let's write it down here. So this term would change to 10, and then the next term would be delta t to the cube over 120, and then here we have a second derivative, and this would be a plus. And then we can replace u dot from the differential equation. It would be lambda u, and then u double dot would be, we can differentiate this equation, so u double dot is lambda u dot, which is lambda squared times u. This equation will become a square here if we replace these derivatives, and then this could become a cube if we replace these derivatives. Okay, so this is trapezoid or the Trapezium rule. This is the Hermite rule, and this is the Lotkin rule. So we see that its approximate gives us an approximation which you can alternatively get with these rules, and you can keep going. You can keep increasing the order by requesting a polynomial that oscillates in higher order in the derivatives, as we learned in the Hermite interpolation and the Hermite integration video. So the reason that this Padé approximation of the exponential function agrees with this is that the solution in this case is exponential. So obviously we can take a time step directly with a solution. So u of delta t is e to the lambda delta t times u0, and then we can make Padé approximants of this e to the lambda delta t and get these approximants directly. But of course, you can only do that if this is a linear equation and you know the solution, that you know that the solution is of this form. But the nice thing about these rules is that they can be applied in any system, in any ODE or system of ODEs, whether they are linear or not. The only difference is that if they're non-linear, then you would have to iterate the equations in each time step. Otherwise, if they're linear, you can solve directly. Okay, so obviously you could get the next order by doing a 4-4 here, or if you go back to the Hermite integration video, you can see how to get higher order rules. So now let's go ahead and implement these schemes and see how they work. So let's define some initial time 0 and some final time, let's say 10. And let's suppose we want to integrate for 100 time steps, and then delta t would be tf minus ti divided by m. And then let's define a range of time instants or grid points in time. We can use range from t initial to t final with step delta t or dt. Okay, so we're going from 0 to 10 in steps of 0.1. Okay, so now we need to define a vector of our solution at each time instant. So we can do that using constant array, initialize our vector to 0. And then let's suppose that the initial condition is 1. And so the first value of u is 1, and the next value will be determined in the loop, in the do loop. So that's what u looks like initially. That's the initial value at the first time instant. And we want to calculate all the future values. We have set them to 0 for now. So we need a do loop. and we will follow these rules. So let's follow the trapezoidal rule first. I can copy paste this result from here. So first of all, we need the value for lambda. Let's set lambda equal to 1. And then u at I plus 1 equals this expression. I have to replace this by dt and this by dt. And then the previous value of u is what multiplies this expression. And then I has to go from 1 up to the final value m. So let's do this and print out u. Okay, so this is what u looks like. Now we can compare this to the analytical result. That would be e to the power lambda times time, and we can simply substitute the time grid here. So these are the values for the exact solution. We see that they are reasonably close for a second order method. And if we want to, we can calculate the accuracy by subtracting them from each other. So let's try that. U minus e to the lambda t. Now we see the accuracy, but we would prefer to have that in relative terms because it's an exponential function, so it increases fast with time. So let's calculate the percent accuracy. Okay, so now we see that the accuracy is at least 2 or 3 digits. And it seems like it's more accurate first. As time goes by, the accuracy decreases a little bit, and we can do a list plot of this to see it. So let's do list plot. And you can see that the error increases gradually with time. In a way that we expect for a second order method. Now, if we had used a Runkerkuta method, so let's suppose that we were using a second order Runkerkuta method, then essentially that would amount to doing a Taylor expansion of this e to the lambda delta t. And what we would have, you can show that it's this is the first order term, and then there would be a second order term. We have dt squared here times lambda squared. So you can easily prove this if you apply second order Runkerkuta. So just to compare to that, we did this in an earlier video. This is equivalent to what we did in the previous Runkerkuta video. So let's do that, and you see that the error also increases here, but the error is much higher. So here you see that after the same time you have 0.08, and here the error is around 0.5 or 0.6. Okay, so the reason that this happens is that if you look at the error terms, the Taylor expansion has an error term which is much higher compared to this, which is essentially a 2-point Taylor expansion. So the 2-point Taylor expansion has much lower error terms because there are, if you look at the formula, which we'll show later, there are several factorial terms in the denominator of the error. So a 2-point Taylor expansion is much more accurate than a 1-point Taylor expansion. Another benefit of these formulas, other than the lower error, is that they are time-symmetric. So if you integrate backwards in time, then delta t changes sign, this term changes sign, this term changes sign, this delta t is square, so it does not change sign. So all terms change sign, and in the end you get the same formula. So whether you go forward in time or backwards in time, you get you have symmetry, and that means certain properties of the equation you're solving will be preserved. And we will see later today in this video that energy or symplectic structure can be conserved either on average or exactly by these schemes. And that's in contrast with the Taylor expansion methods, one-point Taylor expansion methods, or Runkerkuta methods, which don't have this symmetry, and so they violate energy conservation and conservation of area in phase space, as we saw in the previous video. So we will see concrete examples of this today. Let's try and do the next approximation. So this one was the Trapezium rule. So let's try and do the next approximation, which would be the Hermite rule. So let's take this, copy it here, and we can add the correction dt squared lambda squared divided by 12, and then let's add this correction here, and let's try, and you see now that the accuracy is much better. We have here it was 0.08. Now we're getting accuracy of around 10⁻⁶ or 10⁻⁷. If we want to compare this with the Runkerkuta method of the similar order, so this is a Hermite rule and it's fourth order accurate. So we could compare it to a fourth order Runkerkuta method. But let's try that. So that would be the first term, second term. You can show that the fourth order Runkerkuta method is equivalent to a fourth order Taylor expansion of the exponential e to the lambda delta t. So that would be 3 factorial lambda cubed, and that is fourth order term with 4 factorial. So let's try this, and you see that the accuracy is sort of comparable, but it's still about 1 order of magnitude higher accuracy for Hermite rule compared to the Runkerkuta fourth order method. And again, the accuracy is better here, but there's also the time symmetry property to consider, which is very important, as we will see soon. So the next order would be Lotkins rule. So that would be this correction, and let's check the signs. So we have a minus here. Okay, so there's a minus here. This will become 10, 10, and this will become 120, and these will become cubes. So let's try this, and now the accuracy improves even further. We have around 10 digits of accuracy. Okay, so now let's move on to a system of ordinary differential equations. So let's consider the harmonic oscillator again. As in the previous video, we have a linear set of equations harmonic oscillator. So Q is the position, P is the momentum, and the equations are Q dot equals P, and that's simply the momentum, which is mass times velocity, and we've set the mass to 1. And this is Newton's second law. P dot, the rate of change of momentum or the acceleration, is equal to the force of the spring, and we set the constant of the spring to 1, so the force is minus kx or minus kq, and k is 1, so the force is minus q. So that's the harmonic oscillator written as a first order system in time. And again, we'll use the shorthand notation that P at time Tn is Pn and Q at time Tn is Qn. And we will integrate this system forward in time by converting these ODEs into integrals and integrate over a small time interval, do a small time step. And we will approximate these integrals again with the Hermite rule. So the lowest order approximation is to use the Trapezoidal rule for these integrals, like so. There's a minus here, so this is what we get. And the next order approximation is the Hermite rule, which is fourth order. That would be the Trapezoidal rule plus a correction, where we have the derivatives here. And in this case, it's the derivative of P, which is P dot at n plus 1 and n. And for this equation, it would be the derivative of Q. So we have Q dot here at n plus 1 and at n. And there's the minus sign from here showing up here. Again, we can take advantage of the fact that we know P dot and Q dot from the differential equation itself. So we can replace P dot by minus Q, and then we get this expression. And then here we can express Q dot by P, and then we get this expression. Again, we run into the same problem that Qn plus 1 and Qn and Pn plus 1 show up in both sides of the equations. So in general, we would iterate these equations. We would do some initial guess for Pn plus 1 and Qn plus 1, then evaluate this expression, calculate Qn plus 1, and then take the new value, plug it back in here, take the new value from here, plug it here, and calculate these expressions again. Calculate new values for Qn plus 1 and Pn plus 1, and then go back, plug them back in, and iterate. And after a few iterations, 5 or 6, mostly 10 iterations, this would converge. And you can do something similar for this case. However, in this case, our system is linear, so we're going to take advantage of that, and we can solve these inequalities analytically. So let's use the solve command, and then the first equation. If we're using the trapezoidal rule, that would be equals, and then the second expression, and equals, because this is an equation. And then the unknowns. So the previous time step is Pn and Qn. These are known quantities. And the unknown quantities are the future steps. These are Qn plus 1 and Pn plus 1. So if we ask Mathematica to solve this system for us, it will return a solution. Because this is simply a linear system which you can solve by hand. And we can simplify these expressions a little bit. Okay, so now if we want to evolve this system forward in time, we can define a time grid similarly to what we did earlier. So some initial time 0 up to some time 10. Let's take 100 time steps, and then the time step delta t is t final minus t initial divided by the number of steps. And then let's define a time grid to store each instant in time. So we go from 0 to 10 in steps of 0.1. So these are rather large time steps, but we're just demonstrating the method here. Normally you would take smaller time steps to have better accuracy. Okay, so let's define some vector to store the values of q and p. That's the position and the momentum. So let's use constant array to store the values of q and p. So we will initialize these to 0, and then let's suppose that our initial data is that initially the first value of q starts from 0, and let's suppose that the initial value of the momentum is square root of 2. Okay, now our do loop will involve doing these two substitutions repeatedly. So let's try this. So let's execute this, and then this would be our do loop. Here I have just copied and pasted this expression and this expression into here, and instead of n I used I as an index, and then q of I is the previous step and p of I is the previous step or the previous value of the momentum, and qi plus 1 and pi plus 1 are the future values of the momentum. And because this is a linear system, we took advantage of that and expressed these in terms of the old values. So what looks like an implicit system of equations here, with n plus 1 showing up in both sides of the equation, has been converted to an explicit system, but without any change in accuracy or any other property. The benefit is that now we can simply do a do loop without having to iterate the equality in each time step. That's the only difference. So this would be easier and faster, but that's only because the system is linear. If the system was not linear, we would have to iterate in each time step. Okay, so let's try this, and let's try and display the solution. So this is q. It looks reasonable, and let's look at p. That also looks reasonable. Now, to compare, we can compare to the analytical solution, but before we do that, let's check if the energy is conserved. So the energy would be q squared plus p squared, and divided by 2. Okay, so this is a very good sign. We see that the energy starts from 1, which is what we had here, and remains very close to 1. So to see how close, let's subtract 1. Okay, so we see now that initially we have machine precision, and gradually we lose 1 or 2 digits of accuracy, and we can see that better by doing list plot. And we see that we have essentially what looks like round-off error. So the method essentially conserves energy exactly, but because we do this floating point operation, which only has machine precision, there is a little bit of round-off error in each time step, which adds a little bit of inaccuracy, and that accumulates. Now, there is a way to avoid this error. One way is to use Kahan summation or compensated summation. But in this case, there is a very easy trick you can do. So you can write these equalities as increments. So qi plus 1, we want to express it as qi plus a correction. and pi plus 1, we want to express it as pi plus a correction. So basically, we want to subtract qi from this fraction and pi from this fraction. So let's try and do that. So first of all, let me clear these quantities that are stored as vectors, and let's subtract q from the first quantity here, or what we had here, and let's subtract p from the second quantity, and then we will add it back separately. So this is what we get. So now we will use these expressions in our do loop. So let's define our time grid again, and let's define our loop again. So every command is the same as before, except now I use these expressions for p and for q. So this is the expression for q that I'm using here. It's simply a matter of copying and pasting and then using the array notation here. And then I subtracted qn, but I'm adding it back separately. And in this expression, I subtracted pn, but I'm adding it back separately. So we want these equations to look like increments. So we only want to add the difference between qi and qa plus 1 in each time step, instead of doing multiplications here. The reason is, if you think about compensating summation, the round of error in these operations is smaller compared to doing it this way. And let's try this loop, and then let's do a list plot of the energy. And if we do this, well, we see that we are very close to round of error. So although here the round of error accumulates, and we go to the minus 16 to the minus 15 to the minus 14, over a long time period, this will accumulate and increase linearly. But in this case, we're staying very close to machine precision, very close to 10 to minus 16. So I highly recommend doing this if you can. And you can do that for linear systems of ODEs, as well as linear systems of PDEs, as we will see in future videos. Okay, so now we see that the energy is conserved to very high accuracy. The reason has to do with time symmetry. We know from Nether's theorem that systems that are invariant with respect to time translations conserve energy. In this case, we have our system has time symmetry, so energy should be conserved, because the equations are not dependent on time. And our underlying numerical scheme respects that symmetry in a discrete sense, in the sense that if I change from t to minus t or delta t to minus delta t, the equations are invariant. And as a result, energy is conserved. It is also helpful to look at the phase space. So let's try to look at a list plot of Q and P, and we have to do transpose to pair up the Q1 with P1, Q2 with P2, and so on, as we've done previously. So if we do that, we get this phase space plot. And now to make it look correct, we can use aspect ratio 1. Now it looks like a proper circle. And then we can also use axis labels, and then use Q and P. Okay, so we can also join them, the points, if we want. But we see a very encouraging sign that this remains a circle. So in the previous video, when we did Runkerkuta, we saw that the Euler method or lower order Runkerkuta methods, they would spiral out or spiral in as you evolve in time. But here we see that because energy is conserved, the radius of this circle is conserved. So this preserves energy, but it doesn't only preserve energy, it also preserves area in phase space. So these trajectories form a circle, and the area of the circle is conserved. You can consider other schemes that are explicit, like the Verlet method. And in that case, you would get an oval shape here where the energy is not conserved, but the area is conserved. And this circle is squeezed into an ellipse, either along this direction or along this direction. So if this circle becomes an ellipse, then this means area in phase space is conserved, but the radius of the circle is not constant, so energy is not conserved. So conserving area in phase space means that the method is symplectic. We will go into detail on that later. But in this case, we see that the Trapezoidal Rule manages to conserve both energy and symplectic structure, which is very good for a lower order method. You can also plot the solution as a function of time. So for example, if we want to plot Q, the position, as a function of time, we can do a list plot and use the time grid T here and Q here. Okay, we don't quite need that aspect ratio to be 1, but we need axis labels. So for axis labels, let's use T and Q. So this is what Q looks like. And it looks sinusoidal, as you would expect. And the momentum looks like a cosine. So the equation, the solution looks correct. To see the accuracy, we can subtract the exact solution from it. So for Q, the exact solution would be square root of 2 times sine of t. And for P, the solution would be square root of 2 minus cosine of t. So let's do that. So we see that the accuracy is only about 2 digits of accuracy. And this is because this is a lower order method. It's only a trapezoidal rule. Although we are conserving energy exactly, that doesn't mean that the solution has the same accuracy. You can conserve energy exactly, but the solution can still have less accuracy, which is consistent with the method we're using. So if we want to lower the accuracy, we have to use a higher order scheme, such as the Hermite Rule, or we can use smaller time steps. But the important thing about conserving energy is that you can evolve this long term without losing qualitative features of the solution, such as this phase space picture looks like a circle and not like a spiral. And if the energy is conserved, then the amplitude of the solution is not going to be too far off the exact solution. And finally, we can repeat this procedure for a fourth order method. This will be left as an exercise, but I'm going to do the first steps. So first of all, here we consider the trapezoidal rule. If we want to do the Hermite method, then we would use these formulas right here. So this solution, let me first clear Q and P, and let's clear delta T. Okay, so now I can take these expressions here and put them here. Let's try this again. Copy and paste here. So that's the expression for Q. That's the Hermite rule for Q. And then that's the Hermite rule for P. We have this correction. Okay, so in each time step you have to iterate this equation and this equation. Again, because this system is linear in this case, we can actually avoid the iteration and just solve it analytically in terms of the unknowns Qn plus 1 and Pn plus 1. So if we do that, Mathematica gives us the solution. And then all we have to do is do a do loop where we implement this equality and this equality, similarly to what we did here with the trapezoidal rule. So we will have slightly more complicated expressions, but these equations are now, this method is now fourth order accurate. So we're gonna have significantly higher accuracy. And again, if you want the method to conserve energy better, avoid round-off error, then you can do what we did before, which would be subtract Q from this expression. So subtract Q from this and subtract P from this, and then add it back separately and just calculate the increment, the change in Q and P in each time step, and then add it to Q and P. So again, this method would lead to much lower round-off error. And then energy will again be conserved to machine precision, because as you can see, these equations are time-symmetric. So if you change delta t to minus delta t, the equations stay the same, as does the original system. Whereas with Taylor methods or Runkerkuta methods, the original system is symmetric with respect to time, but after you discretize it with the Taylor method or Runkerkuta method, the system is not time-symmetric anymore. So you're violating energy conservation and so on. And thank you for watching, and see you in the next video.